When we looked at spring oscillations in episodes 19 through 21, we thought about how the force of a spring always pushes back toward equilibrium. If we add air resistance and a driving force, we can model real-world springs like we use in machines every day. In addition to forces, we can think of the resulting oscillations in terms of the types of energy present in the system. The first kind of energy we need to think about is called kinetic energy. Kinetic energy is manifested in the movement of the block attached to the spring. The higher the speed or the greater the mass, the more kinetic energy is present. We can calculate the kinetic energy of our block as 1/2 times the block's mass times the square of the block's velocity. The block has the most kinetic energy in the middle of an oscillation and 0 at the top and bottom, since the block's velocity is oscillating out of sync with its position. And if we include air resistance, the block continuously loses kinetic energy from this resistive force. The second kind of energy we need to think about is called potential energy. Potential energy is manifested as two objects interacting through a force. In this case, we're interested in the gravitational potential energy between the block and the Earth, and in the potential energy stored in the compression and stretching of the spring. Near the surface of the Earth, we can calculate the gravitational potential energy with a simple equation, given by the block's mass times the strength of the Earth's gravitational field times the block's height above the surface of the Earth. For the potential energy stored in the spring, we take 1/2 times the spring's stiffness times the stretch in the spring squared. The last kind of energy we need to think about is called work. Work is manifested as one object gaining or losing kinetic energy due to an external force. In this case, we have two external forces, the driving force and air resistance. We can calculate work as the product of the external forces with the distance that the block travels in each frame of the animation. The reason we're interested in energy is because the total energy in the universe must remain constant. We call this the law of conservation of energy. For our block, this universal rule means two things. First, if we have no air resistance and no driving force, then the total of the kinetic energy plus the potential energy must remain constant. Second, if we include air resistance or a driving force, then the total of the kinetic energy plus the potential energy will change by the same amount as the work done by these external forces. Now remember, our animation routine is based on forces. It doesn't know anything about energy, and there's no trick set up to guarantee that this rule of energy conservation will apply. So we can use energy to test whether our code is working properly. Here we set up 4 different graphing curves. One for the block's kinetic energy, one for the total of the gravitational potential energy and the spring's potential energy, one for the work done by the external forces, and one for the total of the kinetic energy and the potential energy. Here in the loop, we calculate the 3 types of energy: kinetic energy, potential energy, and work. These calculations are set up exactly like the equations we saw earlier. Lastly, we graph the current value of these 3 energies, plus the total of the kinetic energy and the potential energy. Let's start out with 0 drag coefficient and no driving force. As the block oscillates, the potential energy and kinetic energy also oscillate, but the kinetic energy and potential energy always mirror each other, so that the total energy is always the same value. This graph shows us how the energy changes from one form to another while the total remains constant. Now let's add in air resistance by giving the drag coefficient a small value. As expected, the total energy decreases since the block is losing kinetic energy to the air molecules that it runs into. And the work done by the force of air resistance also tracks downward, accounting for the loss of energy. You'll get to see what happens with the driving force in the activities linked in the description below. You have now learned how to study the various types of energy involved in spring oscillations. Follow the link in the description below to complete a set of activities to help you learn more about energy.